All right, ladies and gentlemen, in this lesson, we're going to extend our knowledge of trig ratios just a little bit further. So if we graph something on our calculator, maybe something like y sine x, y equals sine of x, it will have the domain of negative infinity to infinity. So right now, we can really only study this piece of it. We can study the piece from the smallest angle we can do is pi over 6. The biggest angle we can do is pi over 3. Right, and pi over 4 is somewhere in the middle. So if this function has the domain from negative infinity to infinity, we're stuck on a very small piece of it. So what we're building towards here is being able to evaluate bigger angles and maybe some points with negative results as well. Right, so a bigger angle, we're going to look at 4 pi over 3 here in a second. Maybe that's somewhere down here. And then 13 pi over 6, well, it's even bigger than 360 degrees because it's bigger than 2 pi, right? Well, that's probably somewhere over here. And then we have all of these angles as well over here, where over here we're going to have negative angles. So our goal is to start to study those as well. To do that, we're going to consider, instead of a triangle, we're going to consider a line segment on the coordinate plane. So we have a line segment through this point, and I'm just going to draw the point. Hopefully I count correctly here. So that's the point -7, 4. And we're told that this angle is called z. And we're going to find sine, cosine, and tangent of z. Right? And notice our angle goes down to the x-axis. It's not this angle. That's going to be important later. So we're going to do our usual relationships here. And notice we have two of our sides already. We have a side of 4, and this time our side down here is -7. And then I can do Pythagorean theorem, which gives me 65 because my negative number squared becomes a positive, right? To get my hypotenuse. And then notice we have everything we need to get sine of z, and I'm going to rationalize that just for fun. Cosine of z is adjacent over hypotenuse, and notice this one's going to be negative. I can again rationalize it, but this is the first time we've gotten a negative working with one of these ratios. So we can start to see how we get these points down here below the x-axis. And then tangent of z, notice we're going to do opposite over adjacent, and I'm just going to write that whole fraction as negative. I don't like that negative on the bottom. Okay, so what we see right away is when we consider angles on our coordinate plane, we can start to think of our results as negative trig ratios now. Now in the previous example, we considered a line segment and we just drew in an angle. Now, let's consider just plain old angles. So let's not give a point or anything. Let's just sketch angles here. The convention is I start at x-axis over here in the first quadrant is 0. And then obviously if I just kind of rotate like this would be a 90-degree angle, aka pi over 2. This would be a 180-degree angle, this would be pi. And then this would be 3 pi over 2, that's 270. And then we're back to where we started. So if I draw 4 pi over 3, 4 pi over 3 is bigger than pi, right? In fact, it's pretty close to 3 pi over 2. So I'm going to draw it down here. And notice I didn't declare a scale, right? I'm just kind of using a plain old coordinate plane. Let's make it a little bit neater. And notice I've made a triangle. This whole angle all the way around is 4 pi over 3. But this angle in here is going to be the angle that I consider, right? So notice that angle is smaller, and I've made a triangle out of it to allow me to evaluate my ratio, because we're still going to do just opposite over hypotenuse to evaluate my ratio, right? So then my goal should be to figure out what triangle this is. Well, if my whole angle is 4 pi over 3, then it might make sense to subtract that pi, right? Because that would give me this leftover here. Well, here, I can make a common denominator, funny form of 1, right? And 4 pi minus 3 pi is just pi over 3, right? So that is pi over 3 here. We call this a reference angle. It's a reference angle for 4 pi over 3. And it allows me to evaluate sine of 4 pi over 3. Right? So now I can just say, well, my short side is 1, my hypotenuse is 2, and my opposite is square root 3. So sine of 4 pi over 3 would be root 3 over 2. But wait just a second. Notice I went down here. So my opposite here, just like the previous example, is a negative. So my sine of 4 pi over 3 now is negative root 3 over 2. So this is how we evaluate these. We draw the triangle, right? We draw a reference triangle that is a special triangle. But the trick here is we also have to consider the sine. So when I'm coming down here, I have a negative y value. My hypotenuse always positive. In fact, if I had used, say I had done cosine, my 1 here would be negative as well, based on the quadrant that we're in. In my next example, we're asked to consider an angle that is bigger than 360 degrees, bigger than 2 pi, right? So to get my reference angle, I'm going to do this time 13 pi over 6 minus 2 pi. And notice here, I need to do again common denominator. That's 13 pi minus 12 pi on top. We get then just 1 pi over 6. So here, we'll use a nice contrasting color. My angle here is pi over 6. And notice we're in the first quadrant here. So this one, pi over 6 is a 30-degree angle. So 1 square root 3 and 2. Tangent of 13 pi over 6 is the same as tangent of pi over 6, which is opposite over adjacent, which is 1 over square root 3, or root 3. Okay? So now we can evaluate not only values bigger than pi over 3, but we can evaluate values bigger than 2 pi. So the last thing we need to consider here are special cases. And these are cases where our little triangle strategy from above doesn't work. So that's these angles. So notice if I was trying to find sine of 0, which was included in our domain, right? If I drew that line segment here, I can't make a triangle out of that, right? Same thing if I was trying to find, I don't know, tangent of 3 pi over 2. I'm kind of stuck. So to solve this problem, I'm going to go back to our example where we consider a point, and I'm just going to think about it a little bit differently. So I'm going to give all of these sides names. I'm going to call this side y, I'm going to call this side x, and my hypotenuse, I'm going to call r, right? So then sine of z, and I didn't rationalize, so this would be easier to see, would be y over r. Notice y is just my y value here. Cosine of z would be, obviously, x over r. And then tangent of z would be y over x. And if I use that formula here, so we wanted to consider 2 points, right? We wanted sine of 0, and we wanted tangent of 3 pi over 2. Okay, so if I draw in a line segment here, and notice I've left my scale, so I can just kind of pick one. Well, an easy one to be picking would be, let's make this length 1. This point then would be 1 comma 0. Sine of 0 is y over r, right? Which is 0 over 1, which is just 0. So sine of 0 is 0. Same thing over here. If I draw a line segment, it'd be convenient to make this 1, but it's got to be a negative 1, right? So this would be the point 0 comma negative 1. And then tangent of 3 pi over 2 would be y over x would be negative 1 over 0. So tangent of 3 pi over 2 is undefined. And there we have it. Now we can consider trig ratios of any angle related to our special angles.